Welcome to Lecture 7. Last week we started talking about combinatorics and probability. This week we will finish our study of probability. We'll start with some concepts of probability. We'll talk about conditional probability, and then we'll finish by talking about probability trees. I'm going to start with the ideas of union and intersection. We introduced these back in part 1. A intersection B means everything which is in the set or the event A and also everything that's in the set B or the event B. A intersection B means just the things which are in both A and B. I'm starting with an example using one die. You'll recall that the sample space for rolling a symbol die is the set S containing the numbers 1, 2, 3, 4, 5, and 6. That's all of the possible outcomes we can get from rolling a single die. And we're going to assume that each of these simpler events are equally likely. In other words, we're going to assume that we have a fair die. Two questions. Question number 1, what is the probability of rolling a number which is even and greater than 3? Question 2, what is the probability of rolling a number which is even or greater than 3? We're going to be using unions and intersections. We need two events. Let A be the event that we get an even number, that's 2, 4, or 6. And we're going to let B be the event that the number we get is greater than 3. So B is going to be the set containing 4, 5, and 6. For question 1, what is the probability of getting a number which is even and greater than 3? We want A intersection B. All of the numbers which are even and they're greater than 3. In other words, we want 4 and 6. Now remember, how do we calculate the probability of the event? It's the number of elements in the event divided by the number of elements in the sample space. In the set A intersection B, we have 2 elements, 2 simple events. In the sample space at the top, we have 6 simple events. So the probability of A intersection B is going to be 2 divided by 6, or 1/3. Now let's move on to question 2, the OR question. What is the probability of getting a number which is even or greater than 3? We want A union B. All of the elements in A together with all of the elements in B. That's the set containing 2, 4, 5, and 6. There's 4 simple events in here, 6 in the sample space, so the probability is going to be 4 divided by 6, or 2/3. Last week we talked about the addition principle. That's the number of elements in A union B was the number of elements in A plus the number of elements in B. But there's a risk that we could be counting the same element twice. So to take care of that, we do minus the number of elements in A intersection B. This week I'm introducing a similar formula, a formula for probability. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. So for example, now let's suppose we have 2 dice. We're going to roll the 2 dice, and then I'm asking what is the probability that the sum is either 5 or 10? Question 2, what is the probability that either the sum is greater than 9 or both dice show the same number? Let's do question 1 first. What's the probability of 5 or 10? Well, we need 2 events. Event A will be what happens, or that the sum is equal to 5. So it's either 1 and 4, or 2 and 3, or 3 and 2, or 4 and 1. There's 4 simple events in A. B is going to be the event that the sum is equal to 10. What didn't you understand? Which slide should I go back to? Face-to-face is not possible for this course. Some of your courses are face-to-face, some of your courses will be online, and this course has been decided that it would be an online course. Okay, let's continue. I want to talk about the probability of A union B. We're going to be using the formula in this field. The probability of A plus the probability of B minus the probability of A intersection B. And the first example I want to use for this is the probability of 2 dice. Question 1. What is the probability that the sum is either 5 or 10? Question 2. What is the probability that the sum is greater than 9 or both dice show the same number? Part A, 5 or 10. How can we get 5 from 2 dice? We can get 1 and 4, 2 and 3, 3 and 2, or 4 and 1. There's 4 events here, 4 simple events in this event. How can we get 10 from rolling 2 dice? We could use 4 and 6, 5 and 5, or 6 and 4. There are 3 simple events in this event. The next thing to note is that A intersection B is the empty set. We can't roll a 5 and a 10 at the same time. So we don't need to be worrying about the probability of A intersection B. Instead, all we're going to be doing is the probability of A union B is equal to the probability of A plus the probability of B. So when we have the numbers 4 and 3, how many simple events are in the sample space? 6 possibilities from rolling the first die. There's 6 possible numbers from rolling the second die. 6 multiplied by 6 is 36. The sample space for 2 die has 36 simple events. So the probability of A is going to be 4 over 36, and the probability of B is going to be 3 over 36, or 7 over 36. Now let's move on to question 2. How can we get a score which is greater than 9, or we get the same number appearing on both dice? Let's call these events C and D. First, how can we get a number which is greater than 9? We could have 4 and 6, that adds up to 10. 10 is bigger than 9. 5 and 5, also 10. 5 and 6 is 11. 6 and 4 is 10. 6 and 5 is 11. And 6 and 6 is 12. There are 6 simple events in C. Let D be the event that both of our dice show the same number. So that could be 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, or 6 and 6. So again, we have 6 simple events here. But these 2 events are not disjoint. There's some numbers which appear in both sets. I have 5, 5 in C, and I have 5, 5 in D. I have 6, 6 in C, and I have 6, 6 in D. C intersection D contains 5, 5 and 6, 6. There's 2 events here. Now I'm ready to use the formula. The formula from the theorem is that the probability of C union D is the probability of C plus the probability of D minus the probability of C intersection D. Because there's 36 simple events in the sample space, everything is going to be divided by 36. What are the numbers on the top? The numbers are 6, 6, and 2. So that's 6 over 36 plus 6 over 36 minus 2 over 36. And when we calculate that, we get 10 over 36, or 5 over 18. The next topic is complements. A complement means everything which is not in A, everything which is in the sample space, but is not in A. The theorem for complements, the formula that we're going to be using, is that the probability of an event E is equal to 1 minus the probability of the complement of E. And this is going to be useful for us because sometimes it's going to be easier to calculate 1 minus the probability of E complement than it is to calculate the probability of E directly. For example, a box containing 45 whiteboard markers is delivered to Istanbul Okan University. 9 of these 45 markers are red. The other 36 markers are black. I will be given 10 markers at random, and I'm going to be happy if one or more of my markers is red. What is the probability that your teacher will be happy? So what we could do is we could calculate the probability that I get 1 red marker, and then we could do plus the probability that I get 2 red markers, plus the probability that I get 3 red markers, plus the probability I get 4 red markers, and so on, all the way up to what is the probability that I get 9 red markers. But that's going to be a long calculation. Instead, we're going to use the theorem. We're going to calculate the probability that I will not be happy, that I don't get at least 1 red marker, and then we're going to do 1 minus this. So this is what we do. The event that 1 or more of the markers is red, we're going to call E. We want to calculate the probability of E, but what we're actually going to do is we're going to calculate the probability of E complement, and then we're going to do 1 minus that probability. So what is the probability that all 10 markers that I'm given are black? We know how to do this from last time. How many different ways could I be given 10 black markers out of the total 36 black markers? 36C10. And what is the number of elements in the whole sample space? How many different ways could I be given 10 markers from the total of 45 markers? 45C10, 45 choose 10. And then the probability that we really want is going to be 1 minus this number. 1 minus 36 choose 10 divided by 45 choose 10. And after we calculate that, and I can leave this for you to check, this is approximately 0.92. The probability that at least one of my 10 markers is red is going to be 0.92, or very, very likely. Next example. In a class of 30 students, what is the probability that at least 2 students have the same birthday? I'm going to go back to the previous slide and repeat. We have 45 whiteboard markers. 9 of the markers are red and the other 36 markers are black. We're choosing 10 markers at random, and what we want is, what is the probability that at least one of the markers is red? And what we're going to do is we're going to use this formula. The probability of E is equal to 1 minus the probability of E complement. We want to know the probability that at least one of the markers is red. What we're actually going to do is we're going to calculate the probability that all 10 markers are black, and then we're going to do 1 minus this. So let's put this in mathematical notation. Let E be the event that at least one of the markers is red. So we could have 1 red marker and 9 black markers, or 2 red markers and 8 black markers, or we could have 3 red markers and 7 black markers, or so on. All of the way up to we could have 9 red markers and 1 black marker. What's the opposite of that? What's the opposite of at least one of them being red? The opposite is that all 10 are black. We're going to calculate the probability that all 10 are black, and then we're going to do 1 minus this probability. Okay, so what is the probability that all 10 markers are black? Probability is the number of elements, the number of simple events in your event divided by the number of elements in the whole sample space. How many events, how many simple events are in the whole sample space? That's the same as saying, how many different ways can we choose 10 markers out of 45? And we studied that last week. We know that there are 45 choose 10 different ways to choose 10 markers out of 45. Now instead of thinking about all 45 markers, let's just think about the 36 black markers. How many different ways are there to choose 10 black markers out of the 36 black markers? 36 choose 10. Okay, so now we know the probability of getting all 10 black markers. We're going to use the theorem, the formula for the theorem, which is the probability of E is 1 minus the probability of E complement. The probability of getting at least one red marker is 1 minus the probability that all 10 markers are black, because these two things are opposites. So it's 1 minus this number. And if you use the ideas from last week, we can calculate this as a number, and it's approximately 0.92. Let's move on to a similar example. In a class of 30 students, what is the probability that at least 2 students have the same birthday? And by the same birthday, I'm not talking about the same year. I'm only talking about the same day and the same month. And just to make this a little bit easier, we're going to ignore the 29th of February. So we're going to be assuming there are 365 days in a year, and we're going to assume that each day is equally likely. What is the number of elements in our sample space? Well, the first student could have any one of 365 birthdays. The second student could have any one of 365 birthdays. So that's 365 multiplied by 365. Then we move on to the third student. The third student could have any birthday. So 365 different days. So again, multiply by 365. It's going to be 365 multiplied by 365, multiplied by 365, multiplied by 365, and so on, until we've done it 30 times, once for each of the students. Now, we want to calculate the probability that 2 or more people have the same birthday. And that could be quite complicated to do. It's possible to do, but it's a long calculation. What we're actually going to do is we're going to be calculating the probability that all 30 students have different birthdays, and then we're going to do 1 minus this probability to get the answer that we want. So how many elements are in E complement? Let's count this. Student number 1 could have any birthday, 365 different days in a year, so there's 365 different birthdays. That's student 1. What about student number 2? Student number 2 needs to have a different birthday. We've already used 1 day, so that leaves 364 different days for student number 2. What about student number 3? Student number 3 doesn't have the same birthday as student number 1. Student 3 doesn't have the same birthday as student number 2. So student number 3 has 363 days left that they could have their birthday, and so on. Multiplied by 362, multiplied by 361, and so on. And because we have 30 students, we end on, this is for student number 30, 336. We're doing 365 factorial divided by 335 factorial, or we're actually doing 365 permute 30. How many different ways are there to choose 30 out of 365 if the order that we choose it is important? And then we're ready to calculate the probability that all 30 students have different birthdays, the number of elements in EC divided by the number of elements in S. We don't want that. We don't want the probability that all the students have different birthdays. We want the probability that at least 2 of the students have the same birthday. So we can do 1 minus this number. And after we do this calculation, we find 0.706, or approximately 70%. If you're in a class of 30 students, the probability that at least 2 students have the same birthday is approximately 70%. The second idea for this week is the idea of conditional probability. Sometimes the probability of an event will occur on another event. For example, let's suppose A is the event Ali has cancer and B is the event Ali is a smoker. Then clearly these two are related. Clearly the probability that A occurs depends on B. In this chapter, we're going to be talking about this type of probability, the probability where one thing depends on another thing. And to be able to talk about this, we need something called conditional probability. The probability of A given B, and we write it like this, is the probability of A line B. This means the probability of A if we already know that B occurs. Sometimes we will know if B occurs, sometimes we won't know if B occurs, but if we already know that B occurs, what is the probability of A? And we have a formula to calculate this. The conditional probability of A given B is equal to the probability of A intersection B divided by the probability of B. In this chapter, we're going to be using this formula. This is one of the ones to remember. So, for example, a bag contains red and blue marbles. 2 marbles are drawn without replacement. In other words, we take 2 of the marbles out and we don't put them back in the bag. The probability of selecting a red marble and then a blue marble is 0.28. The probability of selecting a red marble on the first draw is 0.5. What is the probability of selecting a blue marble on the second draw? Given that, in other words, if we already know that the first marble drawn was red? Let's change this into maths. We need two events. The event R will be that the first marble we take out of the bag is red. Event B is going to be the event that the second marble we take out of the bag is blue. And what we're asked for is the probability of B if we already know that R occurs. The formula for from the theorem is the probability of B given R is the same as the probability of B intersection R divided by the probability of R. And the question tells us these numbers. The probability of getting a red marble and then a blue marble, the question says, is 0.28. And the question told us that the probability that the first marble is red is 0.5. So we just put these numbers into the formula, and the answer we get is 0.56. I have more examples to try to explain this idea. Your friend says that when she rolled a die, she rolled an odd number. What is the probability that your friend rolled number 3? So we need two events. Event A, your friend rolled a 3, and event B, your friend rolled an odd number. What do we know? What is the probability of A? We know that's a sixth because the probability of rolling a 3 from a die is going to be 1 over 6, 6 different numbers. What is the probability of rolling a 3 and rolling an odd number? Well, 3 is an odd number, so that's just the same as the probability of rolling a 3, or 1 over 6. What is the probability of B? What is the probability of rolling an odd number? Well, it must be a half. Equal chance of rolling an odd number or an even number. Now we're ready to answer the question. We want the probability of A given B. We know that B occurred because our friend told us that B occurred. We want the probability of A given B. So it's about using the formula probability of A intersection B divided by probability of B. 1 over 6 divided by a half or equal to a third. Now that makes sense because if our friend says that she rolled an odd number, straight away we know that she rolled either 1, 3, or 5. So there's 3 possibilities, equally likely. So what is the probability that she rolled a 3? We could answer this another way. The probability is 1 divided by 3. Let me go back to the previous example again. We're taking 2 marbles out of a bag. And the question says, if we do the first one is red, and then the second marble is blue, is 0.28. We're going to be using that number. Remember 0.28. The question also says that the probability that the first ball we take out of the bag is red is going to be 0.5. So again, we're going to use the number 0.5. Remember that number. We're asked, what is the probability of selecting a blue marble on the second draw? What is the probability that the second ball is blue if we already know that the first marble is red? This is a conditional probability question. We know that something happens. We know that the first marble is red, and we're asked to calculate a probability if we already know that this is true. So we're asked to calculate the probability of B given R. We know that the first marble is red. We know that this occurs. We know that R occurs. So we want to calculate the probability that B occurs given that R occurs. So it's all about using this formula. This is the formula from the theorem, the formula we're going to be using for this type of question. The probability of B given R is equal to the probability of B intersection R divided by the probability of R. And these two probabilities we know because they're written in the question. The question tells us that getting red then blue, the probability is 0.28. And the question tells us that the probability that the first ball is red is 0.5. So all we need to do is 0.28 divided by 0.5. That's the same as doing 0.28 multiplied by 2, 0.56. Now, let's move on. Remember that the probability of A given B, the theorem told us, is the probability of A intersection B divided by the probability of B. We can rearrange this by multiplying both sides by probability of B. That's the same as saying that the probability of A intersection B is equal to the probability of B multiplied by the probability of A given B. Now, A intersection B is always the same as B intersection A. We can swap B and A around. So that means in the formula in the red box, we can also swap A and B. So that says the probability of A multiplied by the probability of B given A. So in other words, these two things must always be equal. Probability of B multiplied by probability of A given B is always the same as probability of A multiplied by probability of B given A. And here it is. And then if we rearrange that, the probability of A given B must be the same as the probability of A, probability of B given A, divided by the probability of B. That's another one of our key formulae that we're going to be using. Let's move on to a more difficult probability question. I understand that this is a difficult one, but let's just see if you can understand it as I go through it. A famous problem in probability is called the Monty Hall problem. And it goes like this. Suppose you're on a TV game show and you're given the choice of 3 doors. Behind one door is a car, and behind the other 2 doors are goats. You can open one of the doors and you can win a prize. You can win a car if you find the car. So you pick a door. Let's say you choose door number 1. The host of this TV game show knows where the car is. He knows which door has the car behind and which doors have the goats behind. Instead of opening your door, instead of opening door number 1, he opens a different door. Let's suppose he opens door number 3 and he shows you that there's a goat behind door number 3. And then he says to you, do you want to pick door number 2? Do you want to stay with door number 1, or do you want to change your choice and have door number 2 instead? Is it to your advantage to switch your choice if you want to win the car? This problem is named after an American TV host called Monty, and it's a probability that confuses a lot of people that haven't studied probability. So let's see how we can look at this. So what are the probabilities? What are the possibilities? The car might be behind door number 1, or the car might be behind door number 2, or the car might be behind door number 3. We don't know. All we see is 3 doors. You choose a door. What is the probability that the car is behind the door that you choose? Well, that's easy, right? Probability that the car is behind the door that you choose is 1/3. That's correct. And then the host opens a different door and he shows you a goat. Now there are 2 closed doors. Behind one of the doors is a car and behind the other one is a goat. What is the probability that the car is behind the door that you chose? So we're thinking about this. There's 2 closed doors and there's 1 car. So clearly now the probability that the car is behind our door is 1/2, right? That's wrong. What? Why? How is that wrong? That's the point which confuses lots of people, and that's the point I'm going to explain now. To explain this, let's look at all of the possible outcomes if we choose door number 1 first. The 3 doors are, they're all the same for this problem, so it doesn't matter which one we choose. So we'll just say we choose door number 1, and the same thing could happen if we chose door number 2 or if we chose door number 3. It doesn't matter. Let's suppose the car is behind door number 1, there's a goat behind door number 2, and there's a goat behind door number 3. And we've chosen door number 1. And let's suppose the host opens door number 3, shows us that there's a goat behind door number 3, and then he says, do you want to change? Do you want to stay with door number 1, or do you want to change and have door number 2 instead? If we don't change our mind, if we stay with door number 1, we win the car. If we do change our mind and we say we want door number 2 instead, then we lose. We just get a goat. The second case is if the car is behind door number 2. We start by saying we want door number 1. The host knows where the car is. So the host opens door number 3 again, and he shows us that there's a goat behind door number 3. And then the host says, do you want to stay with door number 1, or do you want to change your mind and have door number 2 instead? If we stay with door number 1, if we don't change our mind, then we lose. If we do want to change, if we have door number 2 instead, then we're going to win the car. And case 3, let's suppose the car is behind door number 3. Again, we say we want door number 1. The host knows where the car is, so now the host opens door number 2, and he shows us that there's a goat behind number 2. And then the host says, do you want to stay with door number 1, or do you want to have door number 3 instead? If we stay with door number 1, then we get a goat. If we change our mind and we say we'll have door number 3 instead, then we win the car. So look what we have. If we don't change our mind, if we stay with door number 1, then out of the 3 cases, we win 1 time and we lose 2 times. But if we do change our mind, when we're offered. If we change to the other door we're offered, one of these three cases we lose, and the two of them we win. We can see from this table that if you don't change your choice, then you have a 1 in 3 chance of winning the car. But if you do change your mind, then you have a 2 in 3 chance of winning it. Now, as I said, these are the probabilities if we start with door number 1, but it doesn't matter. That doesn't matter. We could do the same type of table if we start with door number 2, or the same type of table if we start with door number 3. And again, the probability would be a third if we don't change our mind, and 2/3 if we do change our mind. Let's think of this problem a different way. Again, let's suppose initially we start with door number 1. So at the start, the chance that the car is behind door number 1 is 1/3. The chance, or the probability that the car is behind door numbers 2 or 3 is 2/3. Let's suppose I asked you a different question. Let's say you could stay with door number 1, or you could have door number 2 and door number 3. Would you change your mind then? Would you have 2 and 3, or would you stay with just door number 1? Well, I think we would have door number 2 and door number 3, because then we know we have a 2/3 chance of winning the car from 2 doors, and we only have a 1/3 chance of winning the car if we stay with door number 1. But we know that at least one of doors 2 and 3 hides a goat. So if the host opens a door and he shows us a goat, then he doesn't give us any extra information. The host always knows where the car is, so he doesn't open a door at random. He always opens a door with a goat. So really, he doesn't change anything. The probabilities don't magically change to a half and a half. They stay what they were before. They stay with 1/3 and 2/3. Let's solve this problem a third different way. Let's use conditional probabilities. This is perhaps a little bit tricky, but let's see if you can follow this. Let's let C be the event that door number 1 has a car behind it, and let C complement be the event that door number 1 does not have a car behind it. In other words, let C complement be the event that door number 1 has a goat behind it. Event E, we're going to call the event that the host opens a door with a goat behind it. What are the probabilities of these events? What is the probability that door number 1 has a goat behind it? Well, it's a third. Okay. So what is the probability that door number 1 has a car behind it? It's a third. The car could be behind door number 1, or door number 2, or door number 3, so 1/3. So that means that the probability of C complement, the probability that there's a goat behind door number 1, is 2/3. What else can we say? What is the probability of E given C? What is the probability that the host opens a door with a goat behind it, given that there's a car behind door number 1? 1. The host always opens a door with a goat. So the probability of E given C must be 1. What is the probability of E given C complement? Again, it's 1. The host always opens a door with a goat. So the probability of E given C complement must be equal to 1. Now that we have these complements, we can start using the formula. At the start, I have the formula from the last theorem. The probability of C given E is the same as probability of C. Probability of E given C divided by probability of E. And if we go through this, if we do the rules and things we're allowed to do, you see that we end up with a third. So what this means is that it doesn't matter if the host opens the door or not. The probability that the car is behind door number 1 doesn't change. It's always a third. It doesn't change to a half. It's always equal to a third. So what's the conclusion? If you go on this game show and if you're given the choice of 3 doors and if you want to win the car, then the conclusion is you should always switch door when you're given the choice. I hope that was a fun little example. It's a famous problem in probability. The third and final topic for today's lesson is the topic of probability trees. It's another way to think about probability. Let's suppose we have 5 balls in a box. We've got 2 red balls and 2 yellow balls. And we're going to take 2 of these balls out of the box randomly. And we're not going to put them back in the box, we'll just take 2 of them out. What is the probability that the second ball that we take out is yellow? To understand this, we can use a probability tree. And it goes like this. We have a place we're going to start, and then we're going to take a ball out of the box, the first ball. And the first ball is either going to be yellow or it's going to be red. What are the probabilities here? Well, there's 5 balls and 2 of them are yellow. The probability that the first ball is yellow must be 2 over 5. The probability that the first ball is red must be 3 over 5. And then we take a second ball out of the box. And the second ball can be either yellow and red. What are the probabilities of these parts of the probability tree? Let's look at this one first of all. So first we take a yellow ball out, and then there's 4 balls left in the box. So 3 of them are red and 1 of them is yellow. So the probability that the second ball is yellow must be 1 divided by 4. Because 3 of the 4 balls are red, the probability that the second ball is red must be 3 divided by 4. Now let's look at the bottom part. First we take a red ball out, and then we have 4 balls left. 2 of them are yellow and 2 of them are red. What is the probability then that the second ball is yellow? Must be 2 over 4. What is the probability that the second ball is red? It must be 2 over 4. Along each one of these branches, we can multiply these probabilities together. So for example, the probability of going yellow, yellow is 2 over 5 multiplied by 1 over 4. That gives us 1 over 10. The probability of going red, then yellow, we do 3 over 5 multiplied by 2 over 4, or 3 divided by 10. From this tree, the probability of going yellow, yellow, plus the probability of going red, yellow, we add these numbers together. 1 over 10 plus 3 over 10, we get 4 over 10, or 2 over 5. The probability that the second ball is yellow is 2 over 5. Let's do another example. Boris and Kia are playing tennis. The first player to win 2 sets wins the match. In each set, the probability that Kia wins that set is 2/3. Find the probability that Boris wins the match. Find the probability that 3 sets are played. Find the probability that the player who wins the first set also wins the match. Here's a probability tree for this problem. The probability of each branch stays the same. The probability that Kia wins is always 2/3, and the probability that Boris wins is always 1/3. So it's going to be 2/3, 1/3, 2/3, 1/3, and so on. As soon as one player wins 2 sets, the game finishes. So if we go Kia, Kia, that's the end of the game. But if we go Kia and then Boris, both players have won 1 set. We need to play a 3rd set, and we need to go on. Either Kia wins the 3rd set or Boris wins the 3rd set, and so on. Along each of these branches of the trees, we multiply the numbers together. So for example, let's suppose we go Boris, Kia, Kia. Multiply the numbers here. 1/3 multiplied by 2/3 multiplied by 2/3. That's the same as 4/27. Okay, now that we have our probability tree, we can answer the questions. The first question is, what is the probability that Boris wins? Let's see, how can Boris win? Well, we could go KBB, or we could do BKB, or Boris wins the match if we go BB. So we want these numbers. 2/27, 2/27, and 1/9. Add these numbers together. The probability that Boris wins the tennis match is 7/27. What is the probability that 3 sets are played? How could the match have 3 sets? It could be KBK, or KBB, BKK, or BKB. We want these 4 probabilities. 4/27, 2/27, 4/27, 2/27. Add these up and we get 4/9. What is the probability that the player who wins the first set also wins the match? We could have KK, we could have KBK. If Kia wins the first set and the 3rd set, then Kia wins the match. Or BKB, or we could have BB. Add these 4 probabilities together and we get the answer 7/9. Another example. Here's a probability tree. Calculate the probability of B. So where's B? B is here, and here, and here. So we want these probabilities. We could have 3/10, 2/5, and 1/3. Or we could do 3/10, 3/5, 2/5. Or I could go to S, 7/10, and then go to O, 1/5, and then go to B, 1/2. Oh, I missed one. Or we could go 7/10 to get S, and then 4 over 5 to get to this b. So we add these together. The probability of RMB, 3 over 10, 2 over 5 multiplied by 1 over 3, and so on. Along each branch, we multiply the probabilities together, and then we add these numbers together. Add all of the branches that we want to use together. And when you rewatch this, you can check this calculation, check that the probability of B is equal to 79 over 100. One final example for today's lesson. Ron Weasley has a bag with 7 blue sweets and 3 red sweets in it. He takes a sweet at random and then he puts it back in the bag. Then he takes a sweet at random and he eats it. Finally, he picks a 3rd sweet at random. Draw a probability tree to represent the situation. So let me repeat. We start with 10 sweets. We take one of these 10 out, and then we put it back in. So still we have 10 sweets. Then we take one of the sweets out, one of these 10 sweets, and he eats it. So now there's only 9 sweets left. And then he picks one of these 9 sweets. Let's draw our probability tree. For the first sweet, we can either pick a blue one or we can pick a red one. 7 of the sweets are blue, so the probability that the first sweet is blue is 7 over 10, and the probability that the first sweet is red is 3 over 10. And then Ron puts this sweet back in the bag, shakes the bag all around, and then he picks another sweet at random. The probabilities are going to be the same, 7 over 10 and 3 over 10. But this time he eats his sweet, so now there's only 9 sweets left. The 3rd sweet he picks out is going to be something over 9. Let's work out these probabilities. If he eats a blue sweet, then that means there's 6 blue sweets left and 3 red sweets left. So the probabilities are going to be 6 over 9 and 3 over 9. And this part down here is the same. If he eats a blue sweet, then the probabilities are going to be 6 over 9 and 3 over 9. Instead, let's suppose he eats a red sweet. Then there are 7 blue sweets, but only 2 red sweets left. So the probabilities are going to be 7 over 9 and 2 over 9. And that's how we draw a probability tree. We read the information in the question and we draw it like this. That's the end of this week's lecture. Next week, there's no lecture because it's exam week. In 2 weeks' time, we will continue by talking about graph theory. Are there any questions?